Now, the next section that we cover this week is section 3.5, which is higher derivatives. Let me change colors. So we let y be equals f of x. So we have given a function which happens to be differentiable. So that means that f prime exists. Now, if f prime of x, we already know is another function. So you may ask yourself the question whether this new function f prime of x is differentiable. If it is differentiable, we may compute its derivative. And we can compute what's called the second derivative. The second derivative of f, denoted f double prime. And this means that, how we computed f double prime is just the derivative of f prime, as we said. This f prime is a new capital F, if you will, and this is f prime of x. So it's just the derivative of this function f prime is the second derivative. And we can actually continue and compute we can continue if the resulting function is differentiable again. As many times as f is differentiable. So I'm just saying the same thing in using different terminology. So just saying that we can continue computing derivatives as long as we can. So as many times as f is differentiable. So this is just a notation for the same thing. So we'll say that f is differentiable n times if we can continue this process of taking derivatives of derivatives. That means that, for instance, f triple prime is just going to be the derivative of f double prime of x, which will be denoted then also as d3 x3 of f. So this n here corresponds to, so the number here and here corresponds to the number of primes here. So when we continue, we don't write n primes here. That's just too inconvenient. So after maybe 4 times, you just simply write n. In parentheses up here. So if you differentiate 100 times, you don't write 100 primes, just f and in parentheses 100. You put that 100 in here, and the alternative notation is dn f dxn. Of particular importance is the second derivative. F double prime is the rate of change of what function? Remember, f double prime is the derivative of f prime. So this is actually telling us how fast f prime is changing. If we think about f, then f double prime tells us how quickly the derivative is changing. The tangent, the slope of the tangent line these slopes are changing. So f double prime measures how fast the tangent lines increase or decrease. So it's this is good information that we'll come back to it some later point in the semester. And it's good information, and it's a good tool that allows us to draw graphs more accurately. So just to give some example, if you have very large f double prime, you may have something like this. So here the slopes are negative, and they're increasing, becomes 0, then positive, and they start increasing very rapidly after that, becoming very very steep. The slopes, I mean the tangent lines are very steep. So here f prime is less than 0. At this point, f prime is equal to 0, and here f prime is very positive. Becomes very positive. So a smaller f double prime means a not so drastic change. So yeah, f prime is increasing still, but it happens over a longer interval. So f prime is still becoming bigger, and this is the case when f double prime is positive. So but other changes may happen as well. So if f double prime is negative, then instead of making this kind of U shape, you'll be going this way, in this direction. The limit case, of course, is something between where you don't bend upwards or downwards, and that's when f double prime is equal to 0, so that means that you have a straight line. But this is just to motivate this discussion. I mean, as I told you, we'll come back to this this drawing of graphs, this graph sketching later on, and we'll deal with it in more detail. But for now, just to mention, because I mean we're computing higher order derivatives, but the most important for us will be the second derivative. This will give us the most information, and we're analyzing, say, critical points, which is something we'll talk about in the next few weeks. Will be this. I mean the information provided f double prime will allow us to classify these critical points. Knowing the sign of f double prime, we'll be able to say whether a critical point is a maximum, a minimum, or something else, or an inflection point. So f double prime is very important. The other derivatives not so much, but for purposes of performing well in quizzes or exams, I'll give you a couple of things that you will need to know. A couple of examples. So, for instance, the first one is find f triple prime of, say, 1 at 1 for, say, f of x equals 3x to the 6 plus x cubed minus x squared plus 17. Okay, so the solution, well, we already know how to compute the derivative of f. I mean, using the power rule, we bring the 6 down here, and we are left with an exponent of 5 minus 1, so 3 times 6 x to the 5th plus 3 times x squared minus 2 x to the 1, which is just x, and plus 0. When we differentiate, a constant is 0. This gives us 18 x to the 5th plus 3x squared minus 2x. So now what happens when we differentiate this again? We need to just look at this function here and take the derivative. If you want to take the second derivative of f, you need to differentiate f prime, which is this expression here. So again, we apply the power rule, and we get 18 times 5 times x to the 4th plus 3 times 2 which is 6x minus 2, and then here well, you get 50 plus 40, was it 90? X to the fourth plus 6x minus 2. And then if we want to find out the value for f triple prime at a point, we need to differentiate this thing again and see what we get for the formula for f triple prime of x. So we need to differentiate this expression f triple prime of x. Again, we differentiate what's in here. So we simply compute 90 times 4 x cubed plus 6 times x. Well, this is just 6, and the derivative of 2 is 0. We're just going to continue here. Well, we'll continue down here if we want. 90 times 4, so that's 360 x cubed plus 6. So what is f triple prime at 1? F triple prime at 1 is 360 times 1 cubed plus 6, or 366. Okay? So that's the answer. So that's the kind of thing that you will be asked to compute. Something here that you have to notice, because this is okay. So this is probably the simplest kind of question so that you may be asked to solve with respect to, coming from this section for the exam, when you just simply ask to compute the derivative n times, and actually specifies 4 times, 5 times, and evaluate at a certain point, and you just have to do this. The other one has to do with an observation here. So here you have a polynomial. So what happens, this polynomial was initially of degree 6. When we differentiate polynomials, we reduce the degree by 1. So now when we took the first derivative, we ended up with a polynomial of degree 5. Then a second time we ended up with a polynomial of degree 4. And finally we ended up with a polynomial of degree 3. So what do you think happens to polynomials eventually if we take enough derivatives? Yeah, you probably guessed correctly. If we take, in this particular example, if we take the derivative, say, 4 more times, well, of course this term will disappear, and we'll compute one derivative, then one extra derivative. We have x squared, then x, then a constant, and then 0. So the higher the higher derivatives of a polynomial are eventually zero. So the zero function. So if you take enough derivatives, you end up with the zero function. So to be more precise, if f is a polynomial of degree k, then the nth derivative of this polynomial is going to be 0 for any n greater than k. So if the degree is 1, so you have x plus 3. If you differentiate that twice, then you get 0. For the previous example, when we started with a polynomial degree 6, we will need to differentiate this 7 times to get 0. So, so a kind of sneaky question would be, I mean, what we may ask you, for instance, for the multiple choice part, to compute the say 1,000th derivative of a very complicated polynomial. But if that very complicated polynomial has degree, say, less than something much smaller than 1,000, say, then you can immediately answer 0. Okay, it's because of this observation here. Another kind of problem that this is actually much more popular, more popular kind of problem. There are many variants, but this is something that I can bet. I mean, you're bound to see in the next exam for the next midterm. Is to find a pattern for the nth derivative of a given function. So y to the fourth, remember y is equal to f of x, so this just means f differentiated 4 times. So we're asked to find the fourth derivative of y equals x to the minus 1, or what is the same as 1 over x. And then the second part is to determine and this is the part that we are going to be asked to do. Determine a general formula for the nth derivative of the function y. Okay, so this is the kind of problem that you should expect to see. So finding or determining a general formula for the nth derivative of a function of x. One more time, something that you're very likely to see in the next exam is you're going to be given a function of x, like a simple function like 1 over x. Some other examples are 1 over x plus 1, sine of x, cosine of x, or cosine of, say, nx. Some combinations of functions like that, or some say e to the x times x. That's another popular one. And to determine a general formula for those, for the nth derivative of these functions. Okay, so keep that in mind. So the solution, y prime of x. Remember, if you write it in this way, as x to the minus 1, we can apply the power rule. And we get minus 1 times x to the minus 1 minus 1, so it's minus 2. Now, y double prime of x is, we'll multiply minus 2 times minus 1, so get 2 times x to the minus 2 minus 1, which is minus 3. Then y triple prime. And now we multiply 2 times this exponent, which we bring down here, remember? So the minus 3 is minus 6, but we're just going to write it like this to find the general formula. Minus 2 times 3 times x to the, and we subtract 1 from minus 3, so we get minus 4. And so y y differentiated 4 times gives us, again, we bring minus 4 down, multiply everything by that, the minus is cancel out, so you get 2 times 3 times 4 times x minus 4, and we subtract 1 from the exponent, so we get minus 5. And so this is the answer for part A. Now, notice here that notice that the signs alternate. So when we differentiate it one time, 3 times, 5 times, we get a negative sign. So the signs are given by -1 to the n. So you see because also when n is even, you get 1. So -1 to the 1 is -1, which is exactly the sign here. -1 squared is just 1, so we get a plus. Then -1 cubed gives us a minus, and then -1 to the 4th gives us plus again, so signs are -1 to the n for every n, right? That's the first thing you want to find the general formula. Now you see happens here. I could have written here -1 times x to the -2. The same thing here, 1 times 2, and I could have also written -1 times 2 times 3, and then 1 times 2 times 3 times 4. You recognize this. I mean, you're multiplying n times n minus 1 times n minus 2 up to down to 1, which is this formula for n factorial. So here, for instance, we have we're taking derivatives once, so we just have 1 factorial. We are taking derivatives twice here. We get 2 times 1, which is 2 factorial. Then 3 factorial, etc. So the general formula then, so for the nth derivative is equal to -1 to the n, which is given by the signs that we just found, n times n factorial. It's n factorial times x to the n minus 1. And you can see here the exponent is -n minus 1. Differentiated once, we get -2. So we subtract 1 to that. The exponent, so we'll subtract 1 from minus the exponent here. 2, we're taking 2 derivatives, so we get -2 minus 1, so it's -3. Yeah, that's fine. Differentiated 3 times, we get -4. And if we keep going on, this is what we're going to get. So that's the general formula for the nth derivative. So these answers part B. And yeah, this is basically it for this kind of problem. I mean, for the kind of problems you will see for the section. In the next video, we'll cover more examples. This is something that is very popular. It is asked often during exams. For the second exam, for second midterm. Okay, so that's it for now.